some superior algebra.
Yeah, the audience mic is now on, so be careful what you say about Thierry's books.
Also, it looks on the very left. That looks like the second half of univalence.
Yeah, it's a framed picture of univalence.
I see.
What's the central connection?
Did you give it to him? Or?
No.
Oh, you know that Steve and I printed out one of those for Vladimir's birthday on a T-shirt, and then he was walking around it in Paris
with that on his.
Yeah, I think it was the exact same font. So maybe this is from Steve.
Okay, I think we're all here. So let's get going again.
Sorry, could you go?
So for the first. Sorry. Okay. For the first talk after the lunch break, it's a pleasure to welcome Thierry Coquand from Sweden, who will talk about sheaf models of type 2.
So you can hear me? Yeah?
Yes.
Okay, so first, thanks a lot for the organizer for having such a meeting. And I'm very glad to celebrate Martin's 60th birthday. So I first met Martin during a Dagstuhl meeting in June 2000. And so it was the last day of the meeting, and we had a very nice evening discussion, very long discussion where Martin explained to me some of his work and on the patch topology. And I was really impressed by how intense Martin was and going in all details of proofs. And yeah, that was really nice. And since then, we had several discussions, so in airports, buses, missing the stop, actually, of buses, because we were in the middle of a discussion during to Padova, and then in Princeton, Oslo. And so thanks a lot, Martin, for all those nice interactions. So since then, as Peter explained yesterday, so we have been starting to work on universes, and this has been also very nice. But this talk will be about sheaf models and choice sequences. And the problem is how to combine the dependent type theory and choice sequences. And this is a topic that I've had several discussions with Martin. So pre-sheaf and sheaf models. So the notion of pre-sheaf and sheaf models is relatively recent, but it already has a very rich history, and it appears in very different contexts. So first we have Beth, Kripke, for designing model of intuitionistic logic, and there the intuitions were temporal and epistemological. Then, completely independently, and a little before, there was a pre-sheaf model, so due to Eilenberg and Zilber, that were using a combinatorial representation of spaces with simplicial sets, which is a pre-sheaf model. And there the intuition is completely different. It's a spatial intuition. And then a little later, so there was a work by Grothendieck on using the big Zariski topos, where we have spatial intuitions. And so the work I want to present mixes these various intuitions. So why are sheaf models important for choice sequences? So usually choice sequences, so they're presented using bare space, so the space of sequences of natural numbers. But I think it's maybe better to first look at binary sequences. So we use a Cantor space instead. Here, I will denote it by C. So C is a set of all functions from N to the set with only 2 elements. And so one intuition is that working with sheaf models over this space corresponds to adding one generic sequence alpha. So I don't know who first had this insight, but it's a very important insight. Maybe it's Dana Scott, I don't know. So intuitively, this generic sequence alpha that we have access in this sheaf model behaves like an unknown but fixed infinite sequence. And we can reason about all sequences simultaneously by reasoning about this generic sequence. And there is a similar situation, so in the Grothendieck school, when you work over the small Zariski topos over a ring, we had one generic prime ideal of the ring, and it's the same idea. So this is a powerful technique for showing uniform continuity as an admissible principle. So if we have a functional from the counter space to 2, which is defined in the type theory, if we apply this function to the generic sequence alpha, we get a tree which witnesses that the functional f has to be uniformly continuous. And this tree is like an oracle that encodes how the functional f interacts with the function alpha. And Martin has a very nice paper describing this. So his paper on effectful forcing. But so when we have a Sheaf model over one space, this does not give a model where uniform continuity holds internally. So what's the intuition? Is that when we apply f to alpha, this only shows continuity as an admissible principle. To get continuity internally, we should be able to generate new independent generic sequences. So intuitively, so what may happen in this model is that the functional f may depend on the generic sequence alpha, and we need to apply f to a new independent generic sequence to get uniform continuity. So that's why people have looked at topology not only over a space, but over a category. And this, it's captured by the Grothendieck site. So we want to capture the fact that at any moment of time, we can have access to a new choice sequences. And this is achieved by working with a category of spaces where the projection map, so from x times counter space to x, corresponds to the addition of a new generic sequence. And if the space is splitted in two parts, then each injection map corresponds to the acquisition of a new knowledge about the choice sequence. So for instance, x0 may say the generic sequence, one generic sequence starts with alpha, and the other says it starts with 1. This corresponds to new knowledge that we have about the generic sequence, and this corresponds to a change of space. So in general, a map from y to x corresponds to a change of knowledge. So the two maps, in this case, so starting with 0 or starting with 1, intuitively they form a covering. So in base semantics, eventually we should get the knowledge of the sequence starts with 0 or start with 1. So we should get this extra knowledge whenever we have such a covering. And technically, so this defines a coverage on this category of spaces. And technically, so this defines the Grothendieck topology. And in the corresponding Sheaf models, uniform continuity holds internally. So if we look at this model of spaces, starting with counter space and taking pieces of counter space or taking product of counter space with a space, we can check that in this model, 2 is the following Sheaf. So 2 applied to x is a set of Kloppen subset of x, which is the same as continuous map from x to 2. And we can check that 2 to the n, so the counter space in this model is represented by the pre-Sheaf, which associate to x the set of continuous map from x to c. So 2 to the n is actually represented by c. And its continuous map from x to c is exactly 2 to the x exponential n. And then, so since we have representations, so what happens if we have a Sheaf f and we compute the exponential f of 2 to the n? Since 2 to the n is a Yoneda of counter space, so f of 2 to the n of x is exactly f of x times c. So in particular, if we apply this, we look at the Boolean algebra of Kloppen subset of C. We get, in this way, we get that B to, in this model, so the canonical map from B to the set of functions from 2 to the n to 2 is an isomorphism. And this is a very nice way to state that in this model, any map from counter space to 2 is an isomorphism. So in this kind of model, all functional from 2 to the n to 2 are continuous, and all function from counter space to itself is uniformly continuous. So this is captured really nicely by a purely algebraic statement. And So this is what I want to explain. So it's a uniform treatment of uniform continuity. And this is appears so in particular so in the thesis of Ingo Blechschmidt. So using the internal languages of toposes in algebraic geometry. And in this thesis, so at the end of this thesis, Ingo suggests an axiomatic system for the big Zaristic topos. So one axiom is that you have a local ring, and this local ring should satisfy so what we can call the duality principle, which is that so if you define so local spectrum of A to be the set of R algebra map from A to R, then the duality principle states that for any finitely presented R algebra, the canonical map from A to R to the spec A is an isomorphism. So this has a nice algebraic formulation. And Ingo, in this thesis, notices that we can deduce internally inside this topos several properties of the Zariski topos from this axiom. So a similar remark appears already so in the work of Anderskog in synthetic differential geometry. So he had a comprehensive axiom that looks like this duality principle. So what I want, so a remark is that uniform continuity for choice sequences actually can be seen as an instance of this duality principle. So if we are now in this topos with spaces, so and if B is a free Boolean algebra and countably many elements, B0, B1, then so if we now look, instead of R, we take the Boolean algebra with 2 elements, and we look at the spectrum of B, so the set of all Boolean maps from B to 2, while if B is free on B0, B1, and so on, so the spectrum of B is exactly a Cantor space. So duality in this case, it says that the canonical map from B to 2 to the spectrum of B is an isomorphism, and this expresses internally that any functions from 2 to the n to 2 is uniformly continuous. So in this way. So in the B, so that's really a uniform treatment of uniform continuity. So if we look at this statement in the big Zariski topos, so the duality principle, in the particular case where the algebra A is the one which is a polynomial ring on n variables, so it says exactly that all maps from R to the n to R are given by a polynomial. So it's an algebraic version of Brouwer continuity principle that we can capture uniformly with this duality principle. So all this is very nice, but this is about so higher order logic, and what we would like to have is Sheaf models for type theory. Okay, and this is something so that I learned from Martin, as in and his student Swanji. So while type theory has a natural interpretation in pre-Sheaf models, to extend this interpretation to Sheaf models works for interpreting pi sigma. So we can really mimic pre-Sheaf model for having a model of pi and sigma, but it is problematic for universes. So we are back to the talk of Peter de Beer. So what about universes in pre-Sheaf in Sheaf models? So in pre-Sheaf models, there is no problem, as was found by Martin Hoffman. But for a Sheaf model over a space X, so if we try to mimic what we do for pre-Sheaf models, so if we try to define U of B as a set of sheaves over the open set V, so it doesn't work. So we don't get a sheaf because there is a problem with the patching condition. Uniqueness holds only up to isomorphism, but not up to strict equality. And this issue was known and discussed in Grothendieck's school. And this was a motivation for introducing the generalization of sheaves, so notion of stacks, which is like a groupoid valued sheaves with more subtle patching condition. And similar questions appear when one wants to so patch together structures instead of patching together elements. So we need to consider groupoid valued sheaves, so that are known as stacks. And then we need also to consider two groupoid valued, and then infinity groupoid valued sheaves. And actually the goal of the first part of the famous letter from Joyal to Grothendieck in 1984, the goal of the first part was precisely to build such a model of infinity groupoid valued sheaves. However, this is done in a non-constructive way. And what we would like to have, it's a constructive version of this infinity groupoid valued sheaves. And that's where homotopy type theory comes. So Ingo in his thesis also mentioned the fact that if we want a treatment of higher stacks, which is very desirable, it will probably rest upon a version of homotopy type theory as the internal language of infinity toposes. And so this is exactly what we have been doing with a group of postdocs and PhD students. So we have been developing something similar to what Ingo was doing in the one topos case, but in the type theory, homotopy type theory case. And in particular, what we have discovered is a new axiom, a new principle, complementary to this duality principle, which is local choice, which intuitively says that any surjective map into a space has locally a section. So in general, it's not projective. We cannot build a section globally, but locally we can build a section. And we think, it seems that if we add two duality principles, this local choice principle, we seem to get a complete system of axiom. Okay. So we have at least three different examples that can be developed axiomatically. So one is a big Zaristi topos, infinity topos. And why it's nice to have access to homotopy theory. So one example is we have access to the elegant definition of cohomology groups in homotopy type theory. So that was discussed by Andrew Swan this morning. And it's really nice to have this, so we can talk about cohomology of affine scheme, for instance, or of schemes, and prove that cohomology of affine scheme is trivial. But we have also access to objects that we cannot access to in a one topos, like the type of lines or theorems, such that if we look at affine schemes, they are closed by dependent sum types. And this we cannot formulate in a one topos setting. So we have considered also the light condensate stacks. So with, in particular, an internal version of Dykhoff's theorem, so that says how to compute cohomology of compact order spaces, or analog theorems that affine schemes are closed by dependent sum types. So there it will be that stone spaces are closed by dependent sum types. And there at some point we needed technical lemmas about stone spaces. And so I sent an email to Martin, and Martin was able to complete the proof. So it was really good. So thanks, Martin, for this. And then last example. So it was mentioned by Ulrich yesterday. So it's this example of instead of working with rings, so we work with bounded distributive lattice. And the analog of local distributive lattice, so it's linear distributive lattice. So thanks to ongoing work of Jonas Hofer and Christian Sattler, we now have constructive models of all these examples. And these models are defined in a weak meta-theory. And surprisingly, so one key steps, so the main problem is actually to have the right pre-Sheaf models. So as explained also by, I mean, it's connected to the talk of this morning on that. So the topology, once you have pre-Sheaf models, actually to define the topology, so to get sheaves is actually handled internally very nicely using left exact modalities. So this connects with the talk of Andrei this morning. So in summary, so the goal of understanding better models of choice sequences, so that was also a theme of several papers of Martin. understanding better models of choice sequences has led to unexpected developments, so mixing ideas from intuitionistic logic, algebraic geometry, and homotopy theory. And I think to have constructive model is conceptually important, so we can hope for a development of constructive algebraic geometry. So now it should be possible. So using ideas, crucially using ideas from homotopy type theory. And this research can play a role also when we want to internalize these models. So this connect with Ulrich's talk yesterday. So one example is importance of having, even in a classical setting, if we want to build internally a universe, so it's really important to have a tiny, technically, so what is known as tiny interval. And this is something that comes from the study of constructive models of type theory. So once again, so thanks a lot, Martin, for all this nice interaction, and congratulations for this
Thank you.
this birthday. And I will stop here. Thank you.
Ingo had a question. They sent it in the chat. You should, I think, answer it.
In the chat. So let's see. So I cannot see the question. So I cannot see the chat actually.
Ingo, do you want to just unmute and ask yourself?
I can try. Hello, Thierry. Thank you very much for the talk. I just wondered why you said that it's surprising that we first need to find free sheets. I would say it's to be expected that in order to get sheets, we first need to find a free sheet.
Sorry, I cannot hear.
The question was why you find it surprising that you first need to define pre-sheaves.
Oh yeah, yes. So that's so it was. So this issue was found by Jonas Hofer. So I thought it was unproblematic, but actually, so it's very important that you have so the right notion of pre-sheaf, and what you need technically is that so when you look at pre-sheaf, so what's really important is that equivalence between pre-sheaf. If you have a map between two pre-sheaves, so for these maps to be an equivalence in this model, it should be equivalent to have point-wise, level-wise equivalences. And this is true technically. So, I mean, it's true for classically when you work with pre-sheaf, but in this constructive setting, I mean, you have to work a little to get this right notion of equivalence between pre-sheaf. And that's really the key technical issue that has to be dealt with, and which is very interesting. Thanks for the question.
Any questions in the room?
Yeah.
Yeah, thank you. So you have all these sort of constructive models which are prove this duality principle. Is it clear that you got also type theory with canonicity from this? Or?
Yeah, so I think it's, I mean, since the model are constructive, you can compute with them.
Yeah.
So, but type theory is more, so to have a type theory is more problematic. So is exactly for this issue with pre-sheaf actually, is that you have an infinitary condition. So to get the right notion of pre-sheaf, it should satisfy infinitary condition, and it's not so clear actually to have the right type theoretic setting which captures this infinitary condition. So this is probably connected to the talk of Nikolai later on. I mean, well.
Yeah.
Thank you.
Could you say a little more about the local choice condition? I think I bumped again. I used it in a blog post where I showed that there are no square filling curves in sheaves on the square, where you assume a certain surjection and then you say, oh, it has local sections. There, because we are on a compact space, the cover is finite, which is very helpful. So I just wonder, how do you phrase the local choice?
Yep. In this case, I will say it for the big Zariski topos. So in this setting, so you have a affine scheme. So what are affine scheme? They are a spectrum of finitely presented R algebra. And then you say, so if you take a map, a surjection from a type, and this type doesn't need to be a set. So it can be any type. If you have a surjection from a type into an affine scheme, then in general, you don't have a section, but you can get Zariski cover of this affine scheme, and on each open of this cover, you have a section. That's a form.
Okay, but is the statement that there is a Zariski cover, is that an external statement? So
No, it's an internal, internally.
Okay.
It's an internal statement, yes. Yeah.
Okay.
So that's...
There are no very pressing questions, then I think it's time to thank Thierry again.